Good afternoon, everyone. Welcome to the fifth seminar in our department's research seminar series. My name is Zbigniew Wasilewski, and I am a professor in the Associate Chair for Research in the Department of Electrical and Computer Engineering here at the University of Waterloo. I am pleased to have with us today Na-Young Kim. Na-Young is an associate professor in our department and a member of the Institute for Quantum Computing and the Waterloo Institute for Nanotechnology. Her research interests are pretty much quantum all over: quantum electronics, quantum optics, cavity quantum electrodynamics, quantum information and science and technology, and condensed matter physics in general, which really is also quantum. So, Na-Young, thank you for taking the time to speak with us today. And to our audiences, attendees, if throughout the presentation you have questions for the speaker, please enter them in the Q&A function, not the chat, okay, Q&A function. They will be presented to Na-Young during the question period, okay? Thank you, and Na-Young, the floor is yours.
Great, thank you very much for the invitation and kind introduction, Zbig, and also all the support from Andrea and Wes for the smooth delivery of the presentation. I'd like to take this precious opportunity to share my research visions and lessons during this ongoing exciting journey in front of my ECA colleagues and students coming from the broad backgrounds and expertise in the biggest department of the University of Waterloo. So I actually choose to deliver in a high level. Okay, so we are the part of the universe living on Earth, and we all have our own universe in our minds, full of beauties and mysteries. We are surprised and amazed by nature, the infinite plethora of surprises and wonders. We yearn for the stars and galaxies in the space and nature and the artificial entities down on Earth. And also we are looking into deep inside the atoms in the quest of the beauties. As a physicist and engineer, I'm truly thankful for appreciating the beauty and wonders of the nature. In particular, from my training, I have a special lenses to look at the amazing lessons nature teaches us. Throughout the varieties of the conventional and exotic materials, we decipher the hidden codes and the properties inspired by the beautiful and rigorous mathematical expressions and physical laws and principles. Upon the solid and thorough knowledge and understandings, we are able to dream how to turn into our lessons and knowledge into an action by engineering amazing sets of technologies we all currently benefit from. Along this journey, I'm very blessed and lucky to have with my research companions internationally and domestically, overcoming a lot of challenges and also taking opportunities together. At University of Waterloo, these are the people I've been closely working on various exciting research projects, and as well as the international collaborators. So in this talk, I'm going to talk about special focuses on developing novel quantum technologies. And our modern lives are completely different from those 20 years ago, even like 10 years ago, if I remember correctly. Some of the technologies we truly enjoy and exploit are coming from quantum revolutions, such as lasers, transistors, and internets, which we call them as the first quantum revolution or quantum 1.0. And recently, we have been flooded by fascinating news media about quantum computers and communications beyond the academic prototypes, keeping entering into the engineering phases with the gigantic corporates like the IBM, Google, and Microsoft, as well as the startup companies shown in this case as. So we are deep in the second quantum revolution we call Quantum 2.0. So personally, I'm thrilled to be at the heart of this dramatic quantum technology development era, and I'm very thankful to be part of it at University of Waterloo and Institute for Quantum Computing, not to mention the Department of ACE. So in our group, we like to contribute to this field by exploring fundamental properties as well as towards the scalable system engineering. So in particular, we're fascinated by some solid-state materials for the many electrons in the specific atoms, which offer the amazing properties. So here are some of the solid-state materials I've been studying for the last 2 decades. Carbon nanotubes, gallium arsenide, YBCO is one of the high-temperature superconductors, and cuprous oxide. So these have been impacting our modern worlds a lot. And in order to make novel electronic, photonic, you can name it, a lot of different functional devices. So these are made of the single elements. So we're all familiar with this, the periodic table of the elements. And either you can use this, a single element of the atom, or combining different elements in in nature. So in particular, we fabricate electronic and optical devices with the metals and semiconductors, and particularly this group of the elements like carbon, gallium arsenide, and so on. But not only the metals and the semiconductors, in order to make the functional devices, we have to combine with the metals and oxides. So these are what I've been familiar with for the exploring the technologies. So the motivation of one of the quantum technology we are building is to understand what kind of materials, what kind of the knowledges we understand the exotic materials. So as I said, our material domains are the semiconductors and oxides and metals. And today I'm going to focus on the 2 themes of the quantum technologies, particularly the Bloch Exciton-Polaritons and Rydberg Excitons in the context of the quantum simulators. So let's take a simple question. What is a simulator? So I believe everyone is doing the simulation, or simulations are almost happening everywhere, whether you notice or unnoticed, for the weather forecasting, or you're deep in the research projects. So in particular, as a scientists and engineers, we utilize a variety of the different simulations in many different contexts and purposes to support your research or the guiding of your directions. Then next question is, when and where do we perform the simulations? So for example, these photos tells you the evolution of flying simulation tools as a pilot training in the past, but now laymen like us can also experience through a virtual reality gaming product to a sense of the flying experience. In a similar token, we could also build the quantum simulators, which enable us to explore and understand complicated phenomena and problems occurring in nature and universe. So here are some exemplary problems which require the large resources and computing power to address them extensively, like black hole Hawking radiation in space, molecular dynamics in chemistry, or even traveling salesman is the daunting task in computer science, to name a few. So in particular, what we are interested in is what if we could build the quantum simulators to mimic some of the condensed matter materials we've been using. So let's take some moments to think about what we like to simulate deeply, for example, in the materials. What are the materials are made of? So the first thing, we are looking at the materials in terms of particles, the atoms. So this is kind of visionary diagrams of the atoms consisting of the nucleus and the electrons. And electrons has a different orbitals. We all learn in the chemistry early on in the elementary school, the high school, I would say. And there are three aspects in real material, for example, in this particles, and also the orbital functions plays an important role for this, the characterizing the materials. When such atoms come together to form a lattices, like special geometries, like the hexagonal, the lattices for the graphene. So in the right figure is the square lattices, is a kind of the imaginary of the cuprous oxide in the high temperature superconductors, which we believe is the interesting electrical and optical properties coming from this, the crystal structures. And once we have these materials, that what we do, we need to have a characterization tools to understand the electrical, physical, chemical, and mechanical properties. So in physics, the way we see how electrons behave in the crystal structures with the many different detections, I particularly focus on the two methods. One is the angle result, the ARPES, the photo emission spectroscopy, to give us the band structure, how the electron moves in energy and momentum space. So this is the band structure according to the high symmetry points of the crystal structure. And this will tell us how electrons move in the crystals. On the right image is the scanning tunneling microscope to show the electron distribution, how electrons are distributed spatially in the crystal structure. So you can see there's the lattice structures with the intensity of the electrons. So by looking at the band structure and then the distribution of electrons, we are able to understand the amazing properties of the electrons. So that's how we typically do the condensed matter physicists. So when I'm doing this, the quantum simulators, what we are doing is we are exactly mimicking of engineer the particles, in this case, the Exciton-Polaritons. We are using the special techniques to make in the semiconductors. We have artificial orbitals, like very similar to the atoms on the left. And we also engineer the lattices, artificial lattices for this Exciton-Polaritons, many different manners. And once we build, then we can detect how these particles behave in the presence of the lattices with a very similar way. We are measuring the band structures. We are also looking at the electron, the Exciton-Polaritons distribution, the real spaces. So that's how we establish of the quantum simulators based on the Exciton-Polaritons. So let's take a look at what are the microcavity Exciton-Polaritons. But polaritons are usually a kind of general term to refer the photon consisting or dressed with some of the excitation of the materials. In this particular cases, photons are mixed with the electron. And these are sitting in a monolithically grown structure, like microcavity quantum well structures, prepared by the remarkable technology, molecular beam epitaxy. Actually, Zivig is the word expert on this, so we are very good to have him nearby that. And for those of you who are not familiar with what the excitons are, is this. It's nothing but the primary excitation of the semiconductors. So that when we excite the semiconductors with some external manners, like light or the voltage, then we excite the electrons from the valence band to the conduction band, leaving a hole in the valence band. So this oppositely charged electrons a whole are combined via Coulombic interaction because opposite charge, so that they are forming a bound state. That's what we call the exciton. It's very much analogous to the hydrogen atom, so that we call this exciton is the semiconductor analog of the hydrogen atom. And obviously this exciton consists with the electrons and hole, which is charged, so that it is a host of the particle and particle interaction. So we have the monolithically grown the samples. We can confine the microcavity, actually confine the photons like this, the red, the curve for the electromagnetic field at the very highest point of the electric field. We place the quantum well where such bound excitons are residing in. Now we can engineer that these photons and excitons can strongly couple. What does that mean is that the energy of exciton can give the full energy to the photon, but photon can also give back to that. Such kind of energy coupling is reversibly possible within that by as strong as the interaction term, so that we are able to achieve the new quasi-particle we call the microcavity Exciton-Polaritons, which is the quantum particles. And because of this, the inherent nature of the excitons and photons, so exciton you could imagine as a particles, and photon can certainly project the wave, so that this resulting Exciton-Polaritons show the duality of the particle and wave nature, so we could enjoy, and we can also exploit that properties to have that the quantum technology development. And one very nice thing about this Exciton-Polariton is that we are able to access the degrees, internal degrees of freedom in terms of the energy, in terms of the momentum, spin degrees of freedom, interactions. We are able to detect the photons releasing through the cavity. We capture that in the form of the photon, then we can address all the properties quantitatively. So this is amazing direct access to characterize the dynamical aspects of the inside the microcavity Exciton-Polaritons. So this is some of the schematics of how we are evaluating of the properties. And once we have done, what we observe is the band structure or this energy dispersions. And this the strong two bands anti-cross the two branch of the bands is the manifestation of the strong coupling between excitons and photons. And these Exciton-Polaritons are in fact obeying the quantum Bose-Einstein statistics, so that they're very quantum nature. And if you above certain criteria or threshold, then this all Exciton-Polaritons go to the lowest global energy state to forming the macroscopic occupation, which we call the Bose-Einstein condensation, which is also very resemblance to the laser, the coherent lasers. So these are the amazing platform to study fundamental properties as well as the engineering applications. So these are the particles we are working on. And because we are doing this in the semiconductors, and I love semiconductors in the sense that it is dirty, so that it gives us a lot of challenges. But then, as you see, the advanced, the state-of-the-art nanofabrication processing technology help us to really do a lot of different engineering. So I call this the dimensional engineering because we want to make some kind of artificial lattices. So there are a lot of ways to make the engineerable, the man-made of the quantum structures from the zero dimensional. So that means like we could have a quantum dot. So it's literally one atom, like in the periodic table with the streams or the etching techniques, or we can also forming of the lasers with the spatial light modulator or DND, so that we are able to address the single site or quantum dot or zero dimensional structure. We can extend it to the zero dimensional quantity into the higher dimension, like kind of one dimensional systems or two dimensional system as well. So in this particular cases, I'm going to show some of our recent work done in the honeycomb lattices. So let me first point it out that the success of quantum simulator is how much you can control your systems in your way, because in nature, the condensed matter materials are so exotic, but then inside of that, there are lots of different factors are entangled. So it's hard to point out which is the main factor. This quantum simulators gives a solution so that we may be able to only decouple in particular parameters or the factor to identify which is the factor related to or relevant to the properties that we are observing. So in this case, we are designing of this lattices. So the way we do is the honeycomb, so that this is very similar to the graphene. And each site, we set this diameter, and we are using this etching technique. There are several parameters we change. So first parameter is D. So D means is the site-to-site distance. The nearest neighbor, the center-to-center distance is D, and we vary from 3 to 7 micron. So that's the kind of the beauty we can do, because in real material, how you can change this the lattice constant, either you have to have a different different devices, or you have to apply this the pressure or the temperatures and so on. But in this case, we are utilizing this nanofabrication technique so that we can change this the different distance, for example, in these 4 different cases. So, and also, when we make the samples, and this is kind of advanced technologies, but they also help us to control this amount of the exciton fraction or photon fraction for the resulting exciton-polaritons, which quantified it or denoted as the detuning delta. And we vary from -20 to 10. So this does not mean anything, but the negative part you could imagine is the photons are more. So photon dominant the region, or it's a positive detuning cases, excitons are more. So because excitons and photons are different behavior, therefore we are able to see that difference. So these are the parameters we changes. So let's take a glimpse of the experimental data. So we are doing this, the photoluminescence spectra. What does that mean? So photo, so that we have a sample, we shine the laser, so photon, and then our device, the gallium arsenide-based microcavity Exciton-Polariton emits the fluorescence. That's why we call the photoluminescence. We are looking at the luminescence to identify what information in the system, in the presence of the honeycomb lattice, in terms of the momentum, in terms of the energy, and also in the XY plane. So on the left is, I note there's a KX and KY. This is we call a reciprocal lattice, or the momentum space, if you're familiar with the solid state physics. And on the right, what you are seeing is the XY, the real space of the crystal structure you can imagine. So what I'm going to show the movie is a different slice of the energy. So in other words, what you see is kind of tomography of the energy band structure on the left, which is coming very resembling of the ARPAS band structure, the data I showed in the past. On the right is the real space Exciton-Polariton distribution, the intensity, which is analogous to the scanning tunneling microscope images. Let's take a look at the movies. I hope you like it, because as you see, because it's a honeycomb, so there are some kind of structures to show the hexagonal symmetries. So once we have the spectra, what we do is this. So let me go here. In honeycomb structure cases, there's also the honeycomb Brillouin. It's how the symmetry points involved. And we slice this particular direction. This is the energy and momentum, which we call the exciton, the band structure. And this middle is the actually experimental data. And on the right is the theoretical simulation results. You can see that we are able to reproduce what we observe in an experiment. And I think the quality of experiment we have is very similar to the theory, so that I'm very happy about this. And which we call this, the reason we call the Bloch Exciton-Polaritons is they are obeying the translation invariance in the crystal structures in the honeycomb lattices, and so-called satisfying the Bloch theorem. So that's what I call as a Bloch Exciton-Polaritons in the lattices. So the way what we are doing this is we are aiming to do some kind of Hamiltonians with the Bloch Exciton-Polaritons. For example, in this, the Hamiltonian is giving some kind of kinetic energy, how this Exciton-Polaritons are moving around in the sites, which is telling by the first term. And the second term is when we put the Exciton-Polaritons together at the same site, how they're interacting. So that's kind of the interactions. So when we look at this, the strength of this, the moving around versus the interaction, and we are able to access some interesting properties of the quantum material. So that's why our goal is to establish this particular Hamiltonian, like Hilbert Hamiltonian in Exciton-Polaritons. So the way we do is that we actually make lots of different samples as a varying the detuning parameters from the top to the down or different sizes. And from there, what we've been so far doing to quantify this little t, which we call the hopping integral, and hopping integral as a function of the different detunings and different number of the different size of the d, so that we can quantify that. So we are pretty much ready for this, the first term to establish. And now what we are doing is to understand the self-energy concept in the condensed matter, so that if we are quantifying the self-energy, then we may be able to have a route to quantify U for the complete of the Hamiltonian. So this is the current status of that. And this slide, I'm going to show a little bit of that what we are doing in the theoretical part. So as an experimentalist, we're not doing only the experiments, we do also some kind of interesting theoretical modeling. So this is quite deep inside, but then particular blue detune. So as I said, blue means like more exciton. So the more exciton means the exciton can interact more, so that there are some signatures of the exciton interaction. So for example, like this is more like flattened instead of the perfect parabola. And how we can understand this, so that we actually spend about like 12 months. It's like how we can actually understand this. And then like after one occasion of conversation, we know how to do it. Means like we decouple this exciton and photon. So that's what I call this two-flavor Hamiltonian, so that we can expand. So in the very simple case that we treated Exciton-Polaritons as a one entity, then we have 2x2 matrix with some basis. Then we could solve the some theory like this. So as you see, there is some difference, so that we are not very satisfied with this, because maybe qualitatively we can explain some of them, but then I really want to do how we can understand this part, the deviation, so that we take that. So I really thank this Hayden Penn, my first student, and he was also the boldly to expanding this 2x2 matrix into like kind of larger area, so that we have one space for the photons and one space for the exciton. And by this two-flavor Hamiltonian, then now, boom, we have also able to do that. We are very happy about this progress. So this is kind of exciting part. So now where we're headed for this, the Bloch Exciton-Polaritons quantum simulators, is this quantum simulator can benchmark some intractable problems prevalent in, for example, quantum computer science, like the NP-hard optimization. And what we can do is we map the Bloch Exciton-Polaritons into some specific models like Ising Hamiltonians or XY Hamiltonians. And by obtaining the solution of these Hamiltonians, we could map some of the well-known problems like traveling cells problems or the Mexico problem. So that's how we can talk to the computer science colleagues. And on the other hand, we also envision that our artificial engineered Bloch Exciton-Polaritons can be a platform to search topological phases or exotic materials like scarmions or high temperature superconductivities or spin liquids or strongly correlated materials in quantum materials by decoupling some of the entangled factors so that what is a stabilizing factor of the certain phases we observe. So this is kind of the future we are headed for. So let's take one familiar example of the hydrogen atom here, the number one element in the periodic table, consisting of one electron bounded by a nucleus via Coulomb interaction. So obviously we all learned this. So the group of the hydrogen is when electrons are sitting in the ground state of the hydrogen is when the electron is sitting in the lowest orbital states we call is a 1s. But however, if you excite them by some other external energy, then electron can sit in the higher orbitals. So we quantify that is in terms of the n, the principal quantum number. And as I said, the electron is bounded by nucleus by the Coulomb interaction, so that the energy state of each orbital is expressed by very simple binding energy with introducing of the Rydberg constant or Y. So some of you may remember that the hydrogen, the Rydberg constant is 13.6 eV, and in fact comes from the electron charge, electron mass, the vacuum for permittivity, and then the H bar. So that's not only that, but also you could imagine that the group 1 items, the elements like rubidium and cesium, where there's the final valence band, like one last the electron, just like the hydrogen. And in this atom cases, this last electron can go even like any collage, like 70 to 100. So that's what we call the Rydberg atoms. So these Rydberg atoms are really one of the mature technologies to build the quantum computings and quantum communication, so that the origin of the Rydberg atoms technologies, in fact, coming from the beautiful exaggerated properties which obeys the scaling laws as a function of n principal quantum number. So let me summarize some of the properties of the Rydberg atoms in terms of binding energy. As I already showed, that this binding energy is inversely proportional to the n squared. So if n is large, then as you see that the electron is far away from the nucleus, so that you could imagine that the binding energy would be reduced, but that the way the reduction of this binding energy is 1 over n squared. The same thing, you could imagine that when electron is away from the nucleus, then the radius is bigger. Then the orbital radius is the larger proportional to n squared. So that's the scaling laws we do. And utilizing this exaggerated properties, you can also imagine that it is one of the sensitive materials or the devices. You can sense the electric field and magnetic fields and so on. That's beyond this, the quantum technology for the computers. So then you could pause, then is there a way we can make this some condensed matter analog of the Rydberg atoms? Why not? And in fact, indeed, in 2014, there is a seminal paper in Nature reporting, as said, the giant Rydberg excitons in the copper oxide, but the correct name is in fact the cuprous oxide. And in this shiny red single crystal film, by the way, and this single crystal is coming from the Namibia original stone. And it showed that this giant Rydberg exciton, what is it? So I'm just showing just a quick band structure. it is semiconductor, and cuprous oxide is a historic material, which is the first semiconductor to observe the excitons. And it is also actively used to make the solar cells. So it's a quite long-standing semiconductors. As a simple cubic crystal structure, so that its band structure is extremely interesting. So can you imagine that this red colored the crystal can emit the 4 different colors like yellow, green, blue, and violet, depends on which optical transitions between the 2, like 3 valence bands, if I include this, the degeneracy, and then conduction bands. So in this particular talk, I'm going to talk about the yellow, which is the lowest energy transitions. And the Nature paper, it's amazing that what they show is this. Using a very narrow bandwidth of the laser, tunable, like 1 megahertz, and in fact, it's the dye laser, this group managed to observe the N equal 25 Rydberg states at 1.2 Kelvin at low temperature. So this is the world record back then to observe the highest Rydberg end state. And now the N equal 28 below 1 Kelvin is the world record. And if we are in you're in the exciton business, you could maybe sense that N equal 25 is actually amazingly high. It's much smaller than the atomic counterparts like 70 and 80. But in fact, because of the material host, that even N equal 25 of the Rydberg exciton gives the very competitive the optical properties of the Rydberg atoms in the 80s and so on. So this is truly giant Rydberg excitons. And particularly because of the dielectric constant in the presence of the large crystal host, so that the normalized dielectric constant, also effective mass is renormalized as well. So that in this case, the Rydberg constant, the binding energy, is 90 milli-electron volts. So you can imagine that the hydrogen case, you are the 13 eV, but in exciton, in the semiconductor cases, it's like almost 100 times smaller, of 190 electron volts. And the formula is a little bit different from the hydrogen cases because in the semiconductor, so we have to consider this the band gap energy. Right? So from the band gap energy, this is corresponding to the binding. And this the authors show is the scaling laws of the exaggerated properties of the cuprous oxide for the energy state or the binding energy as a function of n, or the spectral line width or the oscillator strength. And also they observe the blockade. So blockade maybe like it sounds pretty fancy, but that means is that because they are so interacting, so interacting is also growing like kind of larger n, so that once you set the exciton, then you cannot set the next one because there's a huge repelling. So that that's what we mean the blockade of the second exciton sitting on top of it. So this is what they observe. Then we are curious about some questions. So one day in 2017, my colleague, the Professor Kyung-Soo Choi, drew my attention to this paper, and we started to discuss what we can do. So I remember also my old friend in University of Tokyo, who's experts of the cuprous oxide in the context of this exciton condensation. So we quickly formed a research team and jump into the completely new world. So I had to learn like how to polish the crystals. I went to Tokyo for 2 weeks. I know how to polish the single crystal, and it was dull color of the black, but if I polish then it becomes the red shiny color. So it was also a very exciting moment. And I also learned how to do the PL and absorption spectroscopy for this a new material. And now, since then I've been busy to establishing the research group and perform this absorption spectroscopy. And while we are preparing for this setups at Waterloo, I was curious what we can do with the sample I made up from this University of Tokyo. And one thought came to hit my mind is that what if we raise the temperature? That what kind of n maximum number of the n we could observe in the Rydberg exciton? So this is the one question that what we can do is like, we scratch our hand and perform some kind of very simple back of the envelope calculation is this. So obviously this is the Rydberg states, the binding energy is about 90 electron volts, and there is a thermal energy. Suppose what kind of thermal energy can break this binding? So it's a simple way from the previous formula, and then we quickly draw the N max as a function of the temperature. Then obviously, if you raise the temperature, then binding energy would be compatible so that you could break it down. So this is kind of the table. So for 1 Kelvin, the record, if you remember, they have an N max is 28. So according to this, the crude estimate expects about 32. And then 4 Kelvin, 16, and then if you go up to the higher temperature, then the N maximum is reduced. And if you go to 100 Kelvin, then you can still able to see this N equal 3. So let's go into the lab. So these are the our lab, and so previous, maybe if I just go once again, so looks a little bit complicated, but then in fact, this is the simpler version of the setup. Basically, you need 3. So one is the light source, and then there is a sample, and then the detector. And we placed the red shiny, I polished it in Tokyo, and especially designed the holder because the cuprous oxide doesn't like this strain, so that I have to, I learned from them, my colleagues, for that the strain-free holder to place into the cryostats, and we perform the absorption spectroscopy in the transmission configuration by varying the temperature from 4 to 100 Kelvin. So that's what we have. And let's see what we see the temperature-dependent absorption spectra. So this is the the spectra at the temperatures. And you see there's 3 main points of the phonon background, and there's 2 groups of the sharp peaks, and which we call this the yellow exciton, and there's a green exciton. So in this talk, I'm focusing on that. And the phonon background is described by well-known the Elliott's formula, basically square root 2 energy. And so that we can subtract the phonon background, then what we left is a beautiful series of the sharp peaks. So let's take a look at that. So what do you observe as a function of temperature? And this, it's a redshift. So when we have a higher temperature, the lattice constant increases so that the excitons states are redshifted and so on, like kind of 3 and 4. So this also notice that the shape of the peak follows the Toyojawa's symmetry Lorentzian formula. So we can fit that to extract the lots of parameters to quantify it. And so this is one of the fitting attempts. And once we have, then we see this temperature dependence of redshift for the band gap, which is related to the lattice constant, also the Rydberg constant as a function of cotangent and hyperbolic in temperature. Now let's see what kind of scaling behavior Rydberg exciton in terms of the temperature. So these are the relevant to the energy states. And at least we are very excited to have a universal behavior of the bound exciton. The binding energy is proportional to 1/n squared. So this is the 1/n squared scaling law. And then the energy state difference, the level spacing is 1/n cubed. And then let's take a look at the table so that on the 3rd column is the maximum, and we could resolve from our detector. The low temperature, we are limited by spectrometer resolution, and a higher temperature is not bounded by our spectrometer, it is reduced by the thermal. So one nice results we think is that even above the nitrogen, the liquid nitrogen temperature, like 80 Kelvin, we are still access the Nmax is about 6. So we are very happy to contribute the small token of the cuprous oxide in the Rydberg Exciton as a different temperature, like a higher temperature. And it gives us a kind of hope that we may develop robust, high temperature Rydberg quantum technology based on the cuprous oxide material. So the future directions we are currently dreaming is in the quantum context is this, the electromagnetically induced transparency. So by using the two lasers, we can control the exciton transition so that this is going to be the basis to establish the qubits, or utilizing the strong Rydberg blockade so we can also develop make the new type of the single photon source, which is also another candidate for the quantum technologies. So that's it for what I've been preparing for. Is in the context of the solid-state quantum platforms, I introduced the Bloch Exciton-Polaritons and Rydberg Excitons. I hope you can have some introduction of that one. And we are now facing the real fun with the preparation, so that hopefully in future we could update you what other further excitements in this one. And in fact, in our group, not only these two themes, but other the research topics we are working on, both theoretically and experimentally, so that I also want to have another opportunities to unpack the research projects that we're working on. So thank you for all your attention. And if you have any questions, I'm more than happy to answer. So thank you very much.
Thank you very much, Nayong, for this great talk. I actually was quite fascinated. Some of them, of course, I did hear, but there were new things I learned. Yes, the talk is now open to questions. So, Andrea, do we have any questions at this point?
Yes, we do. We have our first question. Nayang, you mentioned that we're able to observe many quantum properties in a lab environment using Bloch Excitons Polaritons. What do you think is the nearest practical engineering outcome of such technology out of the lab?
Okay, that's a great question. So as I maybe said that the Exciton-Polaritons are interested in the fundamental work. So the simulators is, you can maybe call now engineering, but then maybe the practical is the one thing you could imagine is the new type of the coherent sources. So in fact, the Exciton-Polariton lasers are another important entities, so that the origin to make this the coherent light source based on the Exciton-Polariton condensation is completely different from the conventional lasers. And in fact, the ZBIG also working on this Exciton-Polariton interband lasers. So we think as the nearest practical application of this Exciton-Polaritons could be such kind of coherent light source. Also, this Exciton-Polaritons have a spin. So here spin is analogous or mapped to the polarization. So depending on the different polarization, there are also a lot of work has been done in the context of the optical switching. So that the very kind of even then some people from the University of Cambridge, they say like kind of femtojoule, the optical switchings based on the Exciton-Polaritons. So those are actually already available, but whether this would be commercial marketable is the different stories. But if you are asking about that kind of context, then the optical switchings, all optical transistors or the coherent light sources and so on. So I hope that would be the answer to your questions.
I do have another question here from Diane Ban. First of all, he says, very nice talk, thank you. And his question is, there's three parts to this question. So first is, how do you prepare the copper oxide sample? That's part one. How thin is the film? And is it a single crystalline structure?
So it's a great question. So I said to polish. So the way it's like we have also polishing machines. So there is a manual. So literally, I actually did shine it with this different sandpaper. So that the different quality of the sandpaper. So we polish it until we have a really atomically the smooth surface. Then you can see this shiny, the red one. This particular films is about 30 microns. So we think it's a 30 microns, but then from our, so we cannot measure because 30 micron is just so tiny so that you can easily break, so that we have to handle really carefully. And then from our experimental data from the Rydberg, the constant, then we estimate the thickness of the film is about 60 micron. We still believe that this preserved the single crystalline structure. Otherwise, we may not see this, the yellow, the optical exciton transitions.
Diane Ban is further asking, have you observed Rydberg Excitons in copper oxide from photoluminescence?
So, okay, so that's also the very deep question. So that's good. And so that I maybe interpret it as a cuprous oxide. So in fact, there are two types of the copper oxide. One is the cuprous oxide, Cu2O, and then also there's a CuO2. So that's the copper oxide. So I actually call it as a cuprous oxide. And Rydberg exciton, this case is, in fact, it's a p orbital. So that because of this band structure, this s orbitals or the d orbitals are prohibited by dipole interactions. So that the photoluminescence cases, what we observe is that the p orbital that Rydberg states are immediately transferred to the 1s, the photoluminescence states through the phonon, because of the phonon background, so that there's a lot of the phonon emissions and the phonon emissions and absorption, so that we have not seen the photoluminescence in the Rydberg exciton states directly because of that. However, what we are also considering is so that's also related to the EIT. And there are the states, because this absorption spectroscopy tells us that where are the states. So in order to emit that Rydberg exciton states, what we can do is design the cavity. So that's our experts and also our colleagues' experts, so that we define the cavity to enhance the emission, like sort of like Purcell effect, then the spontaneous emission that we can able to see. So to my best knowledge, I do not see, but let me, I do. Oh, no, I think there is a recent paper by the Professor Naka in Kyoto University. I think she saw the PL. So let me take my answer back. So the Rydberg, like it's not the highest Rydberg exciton states, but indeed the photoluminescence with the two photon, the photoluminescence, not the single photoluminescence, then they're able to see that one. But if you're interested, I'm more than happy to share that paper. So I think we may see, yeah. But I was thinking about this, the one photon, the photoluminescence, but two photon cases, you can do that.
Do we have any other questions waiting, or can I?
Nothing in the lineup right now, Spig.
So maybe I would take the advantage of this gap here and ask a question or two. So the inspiration in a way behind the Bloch Exciton-Polaritons and the systems was the quantum simulators, and it's pretty hot topic, and I understand it kind of can at certain point solve problems which our computers are stuck on. So how long before they actually do it? Because you were able to explain the observed band structure with your angle resolved, I think, photoluminescence at this point, and you were able to explain that with quantum mechanics, with computer programming. Now what we need to do is construct systems which are tweakable to some extent, and and would be able to answer or faster or answer things which we can't. So how far are we from that?
It's a great question. So that how we can compete with the other technologies, right, for the solving the intractable problems. So in that sense, the Exciton-Polaritons are kind of really the at infant stage, but there are some exciting result I am actually reviewing is that some of the groups in UK, they are building in fact, just the 5-house configuration, which is targeting to solve this max 3-cup problems. And what they did is applying this max 3-cup problems based on the Exciton-Polariton condensates to solve for image fragmentations, like image recognition, or some of the optimization in the circuit, the design. One missing part is that the quantification of the speed and then the resources. So we are not yet ready to estimate how fast or like what kind of thing we can faster than the machines, so that this still needs to be quantified. So thanks for that, the question, and which we are holding that. So not only we just establish and how we can assess the performance of the quantum simulators.
Right. Thank you, Nayak. So one more question then, seeing that we still are no competition here. I was really fascinated with the Rydberg Exciton, and just how many excited states of those excitons were detected in not that low temperature for what we are used to here at Waterloo. So this strikes me like extremely perfect material, because you were of course invoking phonons as the destroyers of those higher excited states, and that's what you were studying to find out how far they will last. But that means that the lattice contamination of this lattice, or even exciton-exciton interactions there are negligible, really, right? Because I say gallium arsenide system, one of the cleanest you can make. Nobody ever got anywhere close to that. So this is quite stunning. Were those things grown with molecular beam epitaxy, and would you know whether the substrates are, like lattice matched? It's there's no way we can grow anything like that because of just the materials involved, but it's just super exciting. Yeah.
Yeah. So I think that's also another great question too. So that this, as I said, the cuprous oxide is the very historic material that people the study for almost like 50 years in the context of the exciton. But then until 2014 of the Nature paper, people are always focusing on the exciton condensation in the kind of 1s states, like ortho states and so on. But in order to see that kind of the exciton condensation, the rule of thumb to observe that is, as you said, the purity. But so far, it's very oddly that the best single crystal actually coming from the Namibia, the natural stone. It's not the synthetic. So people are actually trying the synthetic way to prepare the cuprous oxide, and the quality of the exciton 1s is very, very poor, so that they really digging up to the Namibia. That's special, maybe the area to have that. So this is in fact that the Tokyo colleagues have lots of the stones, so I had to, polish it. But then now I'm actually looking at the different angle. So in fact, the friend in the mechanical engineer who's making this solar cell, he actually gave me the solar cell of the cuprous oxide. So we want to take a look at that. Since we are in the different region, like high end, and perhaps the synthetic cuprous oxide might be still pretty valid. And in fact, there's one paper they see not as good as this N equal 25 or 28 with the synthetic exciton, like cuprous oxide. There's still decent number of the N equal like above 10. So it is quite exciting to also observe that the synthetic material, so that we're also looking into how to prepare that using this oxide chamber to put it in the copper and oxygen and then see. So, but again, like we don't have any manpower, but and then after I submitted this paper, one folks from Australia is like, oh, I like your paper. I have tons of stones here. So that, do you want to have that? And I kind of was like, okay, why not? Like, please send them to me. And so, yeah, so we'll see. Like,
Well, so thanks goodness you cannot excavate the gallium arsenide, because this is we would be out of job. But this is probably analogous to diamonds in some way. It took a while for the synthetic diamonds to really start to approach the quality of the natural diamonds. So I'm really surprised that there is this analog in this cuprous oxide, or well, all right, we'll start digging around. Maybe we can find something even more impressive here. So I don't see any more questions. Andrea, do we have anything, or am I?
No, you're correct. There are no more questions.
No, okay, so I think we're actually very well here on time. 4 o'clock. So Na-Young, thank you so much for this inspiring talk, and I'm so glad you are not far here on the campus. I will be coming with more questions, okay? And of course, I'm looking forward to further collaborations with you. All right. Have a great day, everybody. Thank you for your attention.